Today we're going to spend some time talking about solving inequalities with radical expressions. So before we do that, we have to talk about the different types of domain within a function. We've hit on this when we have graphed the functions, but just by looking at an equation, I can also determine what the domain is. So if I have three different scenarios of functions that I could have right now. The first example is when I have functions that are polynomials. So I want to find the domain when I have the function that's a polynomial. So a polynomial, remember, all my degrees have to be greater than 0. They really have to be whole numbers. So when I'm finding the degree of a polynomial function, my degree is always all real numbers. So hint is the domain is all real numbers, is always all real numbers. So whenever I have just a polynomial, my degree is always going to be all real numbers. And then you notice this number 1 is a parabola because it's x squared, which looks like this. And so my domain is all real numbers, or negative infinity to infinity. If I look at number 2 graphs a line. Again, that's a polynomial, it's all real numbers. Number 3 is a cubic function that looks like this. If you just roughly sketch it, again, my domain is all real numbers because it's a polynomial. So number 4 is a polynomial, and my domain is all real numbers. Okay, so if we go ahead and we scroll, talk about when I have a rational function. So a rational function causes my domain to be a little different. Because when I have a rational function, my denominator is not allowed to equal 0. Because if my denominator equals 0, then I have an undefined expression. So when I have a function that is rational, my denominator cannot equal 0. So how I would do this is to figure out the domain is I'm going to take the denominator, I'm going to set it equal to 0, and my domain is all real numbers except the condition when my denominator is equal 0. So except whenever x equals. So if I look at number 5, if I take my denominator and I set it equal to 0 and I solve, x is going to equal 0, right? Because 0 divided by 2 is 0. So my domain is all real numbers, except x is not allowed to equal 0. Or I could write this in interval notation, like this. And again, I can't have 0 in the denominator because then my answer will be undefined. So whenever I have a fraction, I take my denominator, I set it equal to 0. So number 6, x minus 1 equals 0, so x equals 1. So my domain is all real numbers, but x is not allowed to equal 1. If I wanted to put this in interval notation, it would be like so. So go ahead and try number 7 and number 8 on your own, and then if you have questions, come see me, or you can check the answers on Google Classroom. If we go ahead and we look at the next set of examples, find the domain of each function when it's a radical function, which is really what we're focusing on because that's what this whole unit is. So what do I know about radical functions? Well, a square root function is not allowed to be negative, so I have to take what's in the radicand and I have to make it greater than 0. So take radicand, which is what's underneath the radical house, and I want to solve, oops, if I can spell, I want to solve when x is greater than or equal to 0. Because what's underneath my radical house, I'm allowed to have 0, but I'm not allowed to have a negative number because I can't take the square root of a negative because then that puts me into the imaginary world. So to keep things in the real world, I'm going to take what's in my radicand, what's underneath, and I'm going to set it to greater than or equal to 0. And I'm going to solve, so x is greater than or equal to 0. So since my domain is x is greater than or equal to 0, my domain would be 0 to infinity. If I look at number 10, take what's underneath the radicand, or what's in the radicand, make it greater than or to 0. Solve for x. Now, my domain is 4 to infinity. If I do one more, take what's underneath the square root house, make it greater than or equal to 0. X is greater than or equal to -3, so I have -3 to infinity. So go ahead and if we try this last one, I'll do it with you just because I'm going to have to factor. So make life happy for you. X squared plus 2x minus 15 is greater than or equal to 0. If I factor, I get x plus 5 and x minus 3. So x equals -5 and x equals 3. So when I have to do that, I have to plot it on a number line, and I have to pick the values to the left and right. So if I pick a value to the left of -5, let's plug -6. If I plug -6 into my first factor, it's going to become negative. If I plug -6 into my second factor, it's going to become negative, and a negative times a negative is a positive. If I pick a number between 5 and 3, between -5 and 3, let's pick 0. If I plug 0 into this first factor, I get a positive. If I plug 0 into my second factor, I get a negative, so that's going to be a negative outcome. And if I pick a number to the right of 3, let's pick 6. If I plug 6 in there, it's going to be positive. And if I plug 6 in there, it's going to be positive, and that's going to be positive. So I know what my zeros, they're going to be closed dots because it's greater or equal to. And since it's greater, I'm going where the positives are. So my domain is -infinity to -5, union 3 to infinity. So I only had to do that because I had to factor. So let's now take that knowledge and let's talk about solving radical inequalities. So radical inequalities is very similar to solving all of the rest of the inequalities. We're solving like equations. Solve like equations. But make sure it's within the domain. So if I take number 1, I'm going to solve just like before. So if I wanted to get x by itself, I'd square both sides. So I have x plus 1 is less than 4. So x is less than 3. But now I also have to find the domain. So the domain is what's underneath the square root house set to be greater than or equal to 0. So x plus 1 is greater than or equal to 0. So x has to be greater than or equal to -1. So if I think about this on a number line, if I go ahead and I graph this on a number line, here's 3, open dot, going this way forever, right? It has to have a hard stop at -1. I can't go past -1, otherwise it's going to be in the imaginary world. So my numbers can only be between -1 and 3. So my interval notation for this would be -1 to 3. If I go ahead and I do number 2, I'm going to square both sides. So I have x plus 7 is greater than or equal to 16. So x is greater than or equal to 16 minus 7 is 9. So now I have to take the domain x plus 7, make sure it's within that. X has to be greater than or equal to -7. So if I go over here and I graph my solution, 9 greater than 9 or equal to 9. Notice my domain has to be bigger than -7. So since this is already bigger than -7, I don't have to restrict it. So my interval notation is just 9 to infinity. So in reality, I'm really only having to restrict my domain with my solution when I'm solving an inequality when I have a less than sign, because that's when it could potentially be going into the negative numbers, which could cause my answers to become imaginary. So if I go ahead and I look at number 3, I'm going to go ahead and square both sides. So I have 2x minus 3 is less than or equal to 25. So 2x is less than or equal to 28. So x is less than or equal to 14. So now I'm going to take my domain and I'm going to figure out what that is, what's underneath the radical. So 2x is greater than or equal to 3, and x is greater than or equal to 3 over 2. So if I go ahead and I graph my inequality, this graph right here, 14 is a closed dot going this way, but at 3 over 2 it has to stop, because at 3 over 2, anything below 3 over 2 is going to make this no solution. So my interval notation is 3 over 2 to 14. So I want you to go ahead and pause this video, and I want you to try number 4 on your own. When you finish number 4, unpause and I'll go over it. So the first thing I'm going to do is I'm going to divide by 3. So I have 2x minus 5 is greater than 5. So now I'm going to square both sides. 2x minus 5 is greater than 25. So now I have 2x is greater than 30 and x is greater than 15. Because my solution is greater than, I technically realize that I don't have to restrict my domain because I'm never going to the negative numbers that's going to cause this to be dangerous. But if you want me just to show you, 2x minus 5 is greater than or equal to 0. 2x is greater than or equal to 5. X is greater than or equal to 5 over 2. So x has to be bigger than 2.5, and it is. It's 15. So that's why I didn't even have to do that. So my interval notation is 15 to infinity. So you can go ahead and you can practice some of the problems on the back if you need additional practice. If you feel okay, then I am okay with you stopping.